Hello, my name is Sarah, and I am presenting our recent work in grounded situation recognition. A key goal within the language and vision community is to produce semantic descriptions of images. However, it is not obvious what these should look like. A single classification may ignore much of the image, while object detections capture more of the image but ignore their relationships. Image captioning describes the image more completely, but is difficult to evaluate. A sentence which has the same words as the ground truth but a different semantic meaning may score higher than a sentence with the correct meaning but different words. Situation recognition is a method introduced several years ago which describes images by the primary action taking place in the image. Each action is associated with a collection of between 1 and 6 roles from the linguist author database FrameNet. For example, the roles associated with the verb clipping are the agent who is clipping, the source that they are clipping, the tool that they are using, the item they are clipping from the source, and the place where this is occurring. Each one of these roles has a corresponding value which is specific to the image. While situation recognition eliminates many issues with other forms of image description, it still does not explain where these entities are, which both excludes important information and doesn't allow for things like ambiguity resolution for multiples of the same entity class. For this, we introduced the SWIG dataset and the grounded situation recognition task. In addition to allowing ambiguity resolution, SWIG has many real-world properties such as semantic sparsity and non-human agents. This slide shows an example of a bear as an agent for the verb catching. It is also possible to have inanimate objects as the agent. For example, the action erupting often has the agent of volcano. It can also have absent roles. Looking at the first image of the baseball player, one of the roles for hitting is victim part, but this does not apply to this image, so this role is left empty. The image perspectives are also varied and contain many different scales as well as partial occlusions. This plot shows the varying scales and aspect ratios of a sample of boxes in the dataset. As an example, we chose all the instances of the object class rope. The y-axis is the scale of the bounding box, and the x-axis is the aspect ratio of the box. The colors represent different actions. Some actions, such as tugging or pulling, have very low aspect ratios indicating that the rope object is almost always horizontal when it appears in these actions. For actions like hoisting or climbing, it is almost always vertical. This shows the value in combining groundings and situation recognition, as the action can give a very good prior for the position of the object. This figure shows the scale and aspect ratio for many different object classes. However, these classes are all appearing in the agent role. Here we can see how semantically similar actions like mowing and harvesting or sweeping and vacuuming tend to cluster together, as the agents doing these actions have a similar appearance. It also shows the difficulty of this task, as one cannot just use the agent to distinguish between actions like mowing and harvesting. These agents have an incredibly similar appearance, and these actions must be distinguished using the larger context of the scene. In addition to the SWIG dataset, we defined the grounded situation recognition task and several metrics for evaluating on this dataset. The verb score measures the percentage that the model correctly predicts the action. The value score measures the percentage that the model predicts the correct value for each role. Value all indicates how frequently the value is correct for the entire frame. The grounding value score measures the percentage that the model predicts the correct value and grounding. A correct grounding is a grounding with at least 50% intersection over union, or it can also mean a correct prediction of no grounding in the image. Grounded value all indicates the percentage that the grounding and values are correct for the entire frame. We report all these metrics under 3 settings. Top 1 verb, where the model must predict the correct verb with the highest accuracy. Top 5 verb, where the verb prediction is considered correct if it is in the top 5 most likely predicted verbs. And ground truth, where the verb is given and the model must predict the locations and values. For the top 1 and top 5 verb setting, the values are automatically considered incorrect if the verb is incorrect. We present a baseline and a model which performs this task. For the baseline, we select an architecture from Malya et al., which is designed for the original in situ task. While no longer state-of-the-art, this model has good results while maintaining a simple architecture. We tune the hyperparameters of this model and update the backbone to a modern architecture to further improve the accuracy of this model. We then train a modified RetinaNet object detector to detect all possible SWIG categories. Our baseline is to use the recurrent model to predict the value, and then match each value with a bounding box using the output of the detector. We call this baseline the independent situation localizer, as the situation prediction and detection are trained separately and the outputs are only combined at inference. We compare this to the joint situation localizer, which trains end-to-end to predict the locations and values. While it has a nearly identical number of parameters to the independent situation localizer, it outperforms this baseline across all metrics. The ability to prove across both the grounding and non-grounding scores demonstrate the value in combining grounding with the task of situation recognition. Not only can the context of the situation improve the model's ability to locate objects, but locating these objects improves the model's ability to understand them. Finally, we present 3 extensions: semantic-aware image retrieval, conditional situation recognition, and grounded semantic chaining. For semantic-aware image retrieval, we begin with the query image shown in the first column of this figure. We then use several different methods to get the closest matching images from a collection of potential matches. The first 2 rows shows the retrieved images from the ResNet features pre-trained with ImageNet weights, and from object detections with the SWIG categories. While both of these have people and water, the action taking place doesn't match the action of the query image much of the time. The third row shows the images retrieved from the predicted situation without groundings. The semantics of these images look almost always match, but the perspectives are varying greatly, and the retrieved images look pretty different from the original image. The final row shows the retrieved images using grounded situation recognition. These images match the query image in both semantics and perspective. The next extension we show in this work is conditional situation recognition. In this extension, the model receives as input not only the image, but also a bounding box within the image. The input must include this bounding box as a grounding for one of the roles. These 2 images are both example outputs from this modification of the model. As you can see, when a box around the cell phone is given as input, the model predicts the action as calling and believes the box contains the tool for this action. When the box is given around the baby, the model predicts the action as feeding and believes that this box contains the eater for this action. Here's another example where different query boxes lead to different situation predictions. This leads to our final extension of grounded semantic chaining. The same image can have multiple different situations depending on the query box. However, we know from real life that when there are multiple different situations happening within the same space, they are often related to each other. Because all of the objects are grounded in the image, we can start to connect these different situations. For example, the query of the young boy on the first image produces the prediction that the man is helping his son. However, when the query is around the man, the prediction is that the man is barbecuing. The grounding for the man is the same, so we can start to reason that he is both helping his son and barbecuing. Taking this one step further, when the bounding box is around the family in the background, the model predicts that they are dining on the hamburgers. The groundings for the hamburgers they are dining on is the same as the bounding box for the meat that the man is grilling. Thus, we can reason that the man is helping his son to barbecue and that the people are eating the food that they are barbecuing. Thank you for virtually attending this talk, and please visit our paper for more detailed explanation of this work.